Welcome back to our second part of section 5.4, strong mathematical induction. So consider the example given here. Essentially, g1 is 3, g2 is 5, g sub k is 3, gk minus 1 minus 2, gk minus 2. We will prove that g sub n equals 2n plus 1 for all integers n greater than or equal to 1. So as before, let's go ahead and start out with our base case. Now, in this example, we're not trying to prove divisibility, so we want to verify all pieces that they have already given us. So let's start with g1. g1 is equal to 3, so does, again, g1 equal 3 if we plug into our explicit formula? So we have 2 to the first plus 1. 2 to the first plus 1 does equal 3, so that works so far. And we need to then verify this for g2. Does g2 equal to 5 like they're claiming? g2 equals 2 to the second plus 1. This is 4 plus 1, which gives us 5. They match up again, so we are good to go from here. Now we can move on to our hypotheses. So our hypothesis is going to be that we assume this is true for g sub k equals 2 to the k plus 1 for all integers n less than or equal to k, just as we did in the previous example. Remember, we have to specify this because we are saying that this is going to work anywhere from the start of the sequence all the way up to the kth term. And then our goal is to show this is true for the k plus first term. So for when n equals k plus 1. So again, if we can verify this, then we're good to go from there. Okay, now that we have our base case and our hypotheses labeled, let's go ahead and dive in to our inductive step. Consider for a moment gk plus 1. Based on the formula that they gave us on the previous terms, well, gk plus 1, let's change these out. So that's going to be 3 sub g k, let's see, k plus 1 minus 1 is just k, minus 2 times g, k plus 1 minus 2 is k minus 1. All right. Now, what did we say by hypothesis here? Well, we said that this explicit formula will work as long as n is less than or equal to k. We have k and we have k minus 1, both of which are less than or equal to k. So we know by hypothesis that g sub k equals 2 to the k plus 1, and that g sub k minus 1 is equal to 2 to the k minus 1 plus 1. Since both of these have to be true by our hypothesis, we can go ahead and substitute. So by substitution, we know that gk plus 1 equals 3gk, which is, what did we say gk was? We said that gk is 2 to the k plus 1, so let's plug in. So it's 3 times 2 to the k plus 1 minus 2 times, plug in the next component, gk minus 1 is 2 to the k minus 1 plus 1. Now, if we look closely here and do some algebra, go ahead and distribute and simplify where you can, but we don't have to go too crazy, and you'll see why in a moment. This is equal to 3 times 2 to the k plus 3 minus 2 times 2 to the k minus 1 plus 1. I'm sorry, minus 2 rather. Getting ahead of myself. All right. Now, if we clean this up, this is 3 times 2 to the k. Oops, we missed another distributing there. That should be a plus 3 minus 2 times 2 to the k minus 1 is 2 to the k. And then clean up and combine like terms. We have a 2 to the k here and a 2 to the k here. 3 minus 1, because this has a coefficient of 1, is 2 times 2 to the k. Plus 3 minus 2 is plus 1. And we're in the home stretch at this point. 2 times 2 to the k is 2 to the k plus 1 plus 1. So we have just shown that g sub k plus 1 is equal to 2 to the k plus 1 plus 1, which is the k plus first term. So if we were trying to show for this is true for n equals k plus 1, that's what we have stated. So now we can say, therefore, by strong mathematical induction, we have shown that g sub n is equal to 2 to the n plus 1 for all integers n greater than or equal to 1, which if we look back up at the problem, that is what we were trying to show. And that concludes our second example. Stay tuned for the next part.